Good morning, everyone. I'm Jian from Rutgers University. So today I'm going to present our work VibWrite towards finger input authentication on ubiquitous surfaces via physical vibration. And this is a joint work with my colleague Chen Wang, my advisor Professor Ying Chen from Rutgers University, and Professor Nitesh Saxena from University of Alabama at Birmingham. So user authentication is very important. As we all know, it can verify a user's identity and is deployed at almost everywhere in our daily life. In particular, the increasingly wide deployment of smart access systems requires the authentication process to play a broader role in numerous activities. For example, it becomes very necessary when we want to get the access of the vehicle, apartment building, private devices, secret documents, even some applications in smart homes. And the existing authentication to smart access system mainly rely on the traditional solutions based on the intercom, camera, card, or fingerprint techniques. These approaches, however, involve costly equipment, complex hardware installation, or diverse maintenance efforts. I also want to mention, according to a new marketed research, the deployment of the smart access system is expected to reach the value of $9.8 billion by the year of 2022. So there is a large space left for us to continue to explore in this area. In addition, there is a trend of using low-cost, low-power, tangible user interfaces to support user authentication. Actually, this is not only for the academia, but also for the industry. For example, the token devices such as smart glass, smart pen can be used for associating the identity of their touch interactions. Also, some researchers explore how to distinguish different users using capacitive touch communication between the touchscreen and smart ring. Also, the ultra-sensitive pad can be installed in the vehicle to perform driver authentication to start a car. Actually, these techniques are very convenient to use, but they require the surface being touched by their finger or smart devices to have ability of sensing using specialized sensor or have electrical conductivity. So actually, our work is in line with this low power, low cost trend. And we are exploring how to push the limits of the touch surface. We want to study the probability of converting any solid surface to an authentication surface for the generalized usage. For example, in the movie Mission Impossible 5, that car can be opened instantly when Tom Cruise pressed his palm against the side window. So they they enable the authentication on the side window. Actually, we want to do the similar thing. We summarize our main contribution in high level as follows. We developed the first vibration-based finger input authentication system for the smart access system, which has the capability to work with any solid surface, like this door panel, apartment entrance, car surface, or any surface of the furniture or appliances. Also, the proposed system is able to capture intrinsic human behavior and physiological characteristics from the human finger input, finger touch on the surface, through extracting the unique features from the physical vibrations. Also, we developed a system called WebRide, which has the flexibility to support 3 types of secrets, including PIN number, lock pattern, and simple gestures. So this is done by attaching a pair of vibration sensor and the motor on the solid surface, and we can turn that solid surface into a touch screen. And here it shows a prototype we built, which consists of a low power consumption, low cost vibration motor and the receiver. I'll talk about it later. So let's first take a look at how to make regular solid surface to have ability of sensing, because this is very important. Before do the authentication, we need to let surface to sense our finger touch. The basic idea of touch sensing is to apply low-cost physical vibration into the surface. And this embedded vibration signals can be generated by an attached vibration motor, and we can also attach a vibration receiver on the same surface to sense the physical vibration signals. So the vibration signals can be transmitted from the motor to the receiver continuously. So in that way, any change on the surface, like our finger touch on the surface, can be well captured by measuring the changes of the received vibration signals. Now we know how to make regular surface to have ability of sensing. we know how to sensing, but how to use such sensing technique to perform authentication, to authenticate user and reject attackers. So let's first take a look at the physical vibration transmission property. Actually, it's very similar to the transmission of the wireless signal. When a physical vibration travels through a medium, it experiences the attenuation along the propagation path. When the signal hits the boundary of the finger touch, diffraction and reflection happen. So parts of the signal will be reflected back to the surface, and parts of the signal will travel through the finger, becoming a new wave with different frequency. So finally, all these waves from different paths will get together to the receiver. So such diverse multi-path interference effects can be well captured by the receiver to distinguish different touching locations as well as different touch fingers. And more importantly, how a user performs finger touch in terms of the contacting area, touching force, or even the finger bone structure also plays a very important role on the physical vibration propagation. So we found that the unique features can be embedded in the user's finger input, which can be used to distinguish different touching locations from the same user. We can also use these unique features to distinguish different users, even though they press their fingers at the same location. Actually, this is very hard to use a mathematical model to describe this phenomenon, because there are so many parameters that will affect this physical vibration propagation in practice. But we empirically demonstrate this insight. And from the left figure, it shows a present correlation of the frequency response of the received vibration signals when a user presses his finger at 3 different locations. And we can see such location difference can be well captured by the receiver. And because the same location possesses much higher correlation than that of the different location. Again, we asked 5 different users press their finger at the same location on the surface alternatively. Again, we can still capture the difference from this to distinguish different users because their finger structure or contact area or touching force is different. These important observations demonstrate that the physical vibration properties are strongly affected by the unique human behavior and the physiological characteristics embedded in the user's finger input. So that we want to use all this insight from the physical vibration to do the user authentication to distinguish different people. We also consider the several attack models which are harmful to our system. For example, the blind attack, which is an attacker and adversary can perform randomly touches on the system trying to pass our system. A credential-aware attack, that means the attacker knows the legitimate user's passcode, but for this case, the attacker doesn't possess any knowledge of the WebRide setting details. Also, we have one of the most serious attacks, that is knowledgeable observer attack. That means that the attacker not only knows the passcode, not only knows the legitimate user's passcode, but also observe how the legitimate user input this passcode. And also in our work, we also tested several side channel attacks, including placing a hidden vibration receiver on the same surface or placing a very nearby microphone trying to collect the vibration signals, trying to break our system. So to combat all these attack models, we propose a system which is enable authentication on any solid surface, and we call this system as VibWrite. So to use our system, our vibration motor needs to continuously generate high-frequency vibration signals, and at the same time, our system takes as input the time series of the received vibration signals from the receiver. Then the system performs data calibration, including data synchronization and the clock drift effect mitigation to ensure the received vibration signal always synchronized and reduce the effects caused by the imperfect clock. Also, our system selects and extracts features within a sliding window in the frequency domain. We chose 2 kinds of features: spectral point-based feature and MFCC-based feature, which can well represent the unique features embedded in the user's finger input. And also, our system performs feature selection based on feature score to select the subset of features which have more discriminative power between different touching locations or different touching fingers. And the extracted features are used by 2 phases, profiling phase and authentication phase. in the profiling phase, the feature are extracted when the user presses his finger at a different grid point on the surface or swipe a simple gesture to do the enrollment. And for the authentication phase, for the PIN number and log pattern-based solution, the features are extracted in each sliding window and serves as input to the grid point derivation part and index filtering, and finally we can derive the corresponding passcode from the system. And this passcode, derived passcode, will be compared to the passcode that the user set during the enrollment to decide whether this user can pass our system or not. Independently, our system also enables users to choose simple gesture to swipe their finger on the surface to perform authentication. Specifically, we first identified the useful segment containing the gesture operation, and then we calculate MDDTW distance and the EMD distance to compare the similarity between the performed gesture and the gesture profile. And after that, we use a threshold to determine whether that user can pass the system or not. So the vibration signal being used in our system is really important because our system is based on physical vibration. So the vibration signal generated by our system needs to contain a broad range of the frequency to increase the diversity of the vibration features. Specifically, we first generated repeated chirp vibration signals to linearly sweep frequency from 16 kHz to 22 kHz, which is low noise to our human ears. Also, we noticed that the frequency range of this generated vibration signals is much higher than that of the unrelated noises, making our system less possible to be interfered by some ambient noises. And here shows an example of the generated vibration signals. We can, and its corresponding spectrogram. We can see at the very beginning, we transmit a pseudo-noise pilot, which is used for the signal synchronization. And after a short pause, we generate repeated the chirp vibration signals, sweeping the frequency from 16 kHz to 22 kHz. And the length of each vibration chirp is very short. It's set to 10 milliseconds. So that here, for this example, it's just a half a second example. So that we can see is there are so many vibration chirps sweeping from the 16 kHz to 22 kHz. So in the calibration phase, the timing of the vibration motor and the receiver needs to be synchronized so that we can guarantee the sliding window being used to extract features contain the same parts of the vibration chirp signals. To avoid the uncertainty, we use cross-correlation to compare the PN sequence in the received vibration signals and the known PN sequence to determine the starting point of the received vibration signals and make the signal synchronized. And also in the experiment, we found that the ADC sampling rates may be not a fixed value. There is a small gap between the real sampling rates and the configured sampling rates, so that we use a short calibration phase to estimate the sampling rate offset and make corresponding correction. For the feature extraction, in order to extract unique features, we first use FFT to analyze the received vibration signals in a frequency domain within a sliding window. And the length of this sliding window is set to 200 milliseconds. As our transmitted vibration signals is a repeated signal, it has the fundamental frequencies that are all multiples of the frequency 1/t. So we can see in this figure, the interval between two adjacent peaks is 100 Hz because the length of the vibration chirp in our transmitted signal is only 10 milliseconds. And we found that the amplitude of this frequency of these peaks are the most sensitive part to the small change caused by our finger touch. So we extract this amplitude of the peaks. We call it spectral point as a feature to discriminate different touching locations as well as different touching fingers. And the red figure shows a distinguishable pattern of the spectral points when a user presses his finger at 4 different locations, so that it demonstrates the effectiveness of this feature. Besides spectrum points feature, we also extract the MFCC-based feature. We found that the male frequency capture coefficient actually is widely used to represent the short-term power spectrum of the acoustic signal, and it also has been used in so many voice recognition systems. But we found that MFCC is able to capture the sound difference of different people, but it also can used to characterize the vibration signals transmitted in the medium, because the unique human behavior and the physiological characteristics, as well as the different touching locations, cause different on the physical vibration propagation. So that in each sliding window, we also extract the MFCC-based feature to help us to distinguish different people. In order to do the authentication using pin number and the log pattern, we first need to draw a grid on the surface, and we apply a sliding window to the received vibration signals, and extract the feature in each sliding window. And after that, we use the SVM-based grid point classifier to estimate the fingerprint, the finger touch position in terms of its the grid point index. We also devise a method to perform grid point index filtering to select the segment that contain the consecutive same grid point indices. And after that, we derive the passcode. For example, for this example, x-axis is the sliding window index from 0 to 100, and the y-axis is the grid point index, where E represents the empty phase, and 1 to 9 are corresponding to the 9 virtual points in this figure. And for this example, actually, we ask the legitimate user presses his finger at 1, 2, 6, 7, and the blue curve are the classification in each sliding window, and the right segment actually are the segment we use to represent the consecutive same grid point indices. And we derive the passcode 1267. Actually, this matches with the passcode that the user set during the enrollment, so the user can pass the system. Similarly, when the users perform swipes on the surface through the number 1259, our system can also correctly identify these numbers that the pattern passes. But differently for the attacker, it's not that easy, because our system uses attacker's vibration signals according to the legitimate user's profile. So we observe that nearly all the physical vibrations are mistakenly classified, because they don't match between the legitimate profile and the attacker's vibration signals. Even though the attacker pressed the exactly same number, 1267, but finally our system identified it as 1548. Actually, this demonstrates our system, the effectiveness of our system. We have integrated both passcode and the unique human behavior and physiological characteristics together to enhance our system. Again, for the authentication using gesture, our system also enables users to perform simple gesture on the surface to perform authentication. Specifically, we'll first use feature difference to do the gesture recognition, to do the gesture segmentation. And after that, we extract feature in each sliding window. And also we use two kind of methods, DTW and EMD, to measure the similarity between the performed gesture and the gesture profile. And we use a threshold to determine whether that user can pass the system or not. For the experimental setup and the prototype, we evaluate our system in a 3x3 square-shaped grid, which is drawn on a solid surface in a typical office environment. Actually, we tested two different surfaces. One is with the vibration motor and the receiver on the wooden table. The other one is on the door panel. And we also built a prototype which consists of a pair of vibration receiver and the vibration motor. For the vibration motor, it is implemented by a linear resonant actuator-based motor. And for the receiver, it is implemented by a piezoelectric sensor and a low power consumption amplifier, which can be easily plugged to any recording device to sense the vibration signals. Again, we found the size of these two sensors is quite small, so we can easily attach these two sensors on any solid surface to enable our authentication. For the data collection, we recruit 15 participants across different days, and totally we have a 450 genuine input passcode collected for each receiver and transmitter setup. We also collect more data for each attack model. For the performance of verifying a legitimate user, we found that the PIN number-based authentication can achieve very good accuracy. Specifically, the user can achieve over 95% verification accuracy to recognize each PIN digit, and over 90% accuracy to recognize the whole PIN sequence. And right figure shows the average verification accuracy along with the different number of trials until success, we found that for the log pattern-based based solution, the accuracy can achieve about 95% if the system allows 2 trials. Also, we test the robustness of our system on the various attacks. For example, one of the most serious attacks is knowledgeable observer attacks. For this attack, the attackers not only knows the legitimate user's passcode, but also observe how the legitimate user input the passcode. So for this very serious attack, our system can still get very good accuracy to reject these attackers. For example, the attackers can break the pin sequence with only 2% accuracy, and the log pattern with only 5% success rate. So all these results actually demonstrate our system can effectively verify the legitimate user as well as reject the attacker. Even for these very serious attackers, knowledgeable observer attacks, our system still have a good accuracy to reject them. To conclude our work, actually in this work, we proposed VibWrite, which is the first vibration-based finger input authentication, which can be used on any solid surface. And also, we demonstrate that the physical vibration can be used to capture the unique features embedded in the finger input on the surface. Also, we implemented a prototype which consists of a pair of low-cost, low-power consumption vibration receiver and motor to support our system. Also, we demonstrate the robustness of our system on the various attacks. Demonstrate that our system is very effective to authenticate legitimate user and reject the attackers. So for the limitation of the future work, actually, the current version of this VibWrite is just an academic prototype. It's not ready for the practical deployment in terms of its accuracy as well as attacker rejection rate. So in the future, we need additional efforts to further improve our system. For example, we can consider to deploy multiple sensors instead of one pair of piezoelectric sensor to increase the diversity of the vibration features. Also, we can further refine the hardware because the hardware is very crucial in this part. It can process the very weak signal. So we need to further refine this to improve our system. Also, we can consider to improve the authentication algorithm. For the additional physical attacks, actually in our paper, we have already considered the side channel attacks, including placing a hidden vibration receiver or placing a nearby microphone to break our system. But in the future, we need to consider more physical attacks, including this DOS attack or just a physical attack. Just for example, we can just cut the cable directly. And for the system maintenance, right now, all the experiments are conducted in the indoor environment, that environment is very stable. But in the future, we'll definitely try the outdoor environment. But for the outdoor environments, there are many environmental factors will influence our system. For example, different temperature, different humidity, weather conditions, even the dirt or other conditions. So we need to consider all of them. So for example, we can consider to use directional sensing technique or further filtering to narrow the sensing zone to address this problem. Also, we can consider more robust classifier, machine learning classifier like deep learning to help us to distinguish different people or perform authentication in outdoor environments. That's all, thank you. I'm glad to take any questions.
Okay, thank you, nice presentation, nice work. Two quick questions. One is, perhaps you said it and I missed, what exactly separates you from commodity hardware? That is, how much over a current commodity device like a vibration-capable phone are you removed, right? So what would you need? What would you need from a commodity device to be able to do this? That's my first question. The second question is, I saw you conducted experiments on a flat surface and on a door, on a vertical door. Have you considered experiments on angled surfaces, and moving surfaces where, like, I'm holding a device in my hand and I'm trying to do this?
Okay.
So.
Yes, thanks for your question. It's actually a very good question. So for your first question, right now, all the hardware we develop, for example, the vibration motor and the vibration receiver, is just obtain the data from the depth sensor. After that, of course, we need a further like a computer folder and a processor to process the data, to run our classifier, to extract feature and estimate the finger price to derive the passcode. So if you ask the cost of this sensor, we estimate that if we have built a complete system, a complete user authentication system, the cost should be within the $50 range. And for the second question, right now we tested the vertical and horizontal surface, but for the angle surface, I think for the angle surface we didn't try that, but it should work because it's stable. But for the movable surface, I think it would be very challenging because overwork, we actually one of the crucial factor is the touching force. So we do require the user to make it consistent every time because this definitely influences the physical vibration. So for the movable surface, I think for the user it would be very hard to make a consistent touching force on that surface. That's one thing.
There are scenarios clearly, right, where the surface is moving.
Yeah. Right? Yes. Thank you.
David Coates, Dartmouth. Nice work, very creative idea. To his point, you tried both a vertical door surface and a horizontal desk surface. My understanding is that touching the surface anywhere will change the vibration pattern that's picked up by the vibration receiver. Is that right?
Yes.
So if you're testing a desk, for example, and I put down my cup of coffee in order to input the PIN code, it doesn't work, right? Because the cup of coffee has changed the surface, and so it seems, if I understand correctly, this only works for surfaces that do not change except during the input of the secret. Is that right?
Yeah, yeah, you're right. Overwork actually is aimed on the smart access system, which most of them are like a door panel. Most of them are vertical surface. But for the flat, like the table, if there is a temporary object placed on the table, like the coffee, a cup of coffee, it will definitely affect our system. So
smart access systems that are vertical.
Yeah,
is that right?
Yeah, I'm not saying that, but
you are saying that. I just wanted to clarify. Okay.
Yeah. Yeah, but you're right. But you're right.
Smart access systems that are vertical. And my other question is about you sort of make three claims, basically. One is that I can detect your system can detect where I'm touching. Two is that you can detect my behavior, for example, my touch force. Assuming I'm consistent, it should work. And the third is that you're detecting some physiological property of my finger. And frankly, I'm not really convinced about that last piece. I don't think your data really separates physiological differences from, for example, touch force, or I just don't think you have enough data about enough people in order to make that claim. Can you explain that a little bit?
Sure. Actually, in our experiments, we asked multiple participants press their finger at the exactly same location, but we can see the difference from the received vibration signals. But you are right. Some finger structure or some physical characteristics corresponding the finger touch, that is unique, but that is not that unique because in our experiments we found that some attackers' input can still be correctly identified.
Sure. So
yeah.
all I'm saying is that I think in order to really validate that claim, you need more data.
Yeah.
Okay.
For sure. Thank you.
So I'll ask one final question. One of the common attacks on gesture-based authentication for cell phones is this smudge attacks, where you look at the smudge and kind of infer the gesture. Do you think this new system, VibWrite, could be used as defense against such attacks, given that you can kind of pick and choose the surface?
Yeah, for sure. Actually, this is a very good point. For the touch screen, the one very important attack is smudge attack. But for our system, we want to enable authentication on any solid surface, like the door panel. But for the door panel, it's very hard to capture the smudge on the door. So that is one benefit for this system compared to the touchscreen-based authentication system.
All right, let's go ahead and thank Jian.
Thank you.